Today, we delve into the world of linguistic subtleties, uncovering the secret of one of the most treacherous grammatical traps in the English language. We're talking about the eternal struggle between the words less and fewer, whose incorrect usage can confuse even experienced native speakers. Many of us, at times, unthinkingly use less where fewer should be, and vice versa. But there's no need to despair. The rule governing their use is surprisingly simple and logical. Remember, fewer is the faithful companion of countable nouns, those that can be counted individually. Less, on the other hand, is the devoted ally of uncountable nouns, those that appear to us as a mass or volume. Imagine juicy apples lying on a counter. We would unhesitatingly say, fewer apples, because each one can be picked up and counted. But when it comes to water, that elusive element, we use less water, emphasizing its continuity and lack of distinct boundaries. To solidify this knowledge, let's look at a few more vivid examples. On city streets we see fewer cars, not less cars, because each car is a separate object. And when time is short we say less time, not fewer time, feeling it as something ephemeral and uncountable. Mastering this distinction is key to precise and articulate communication. While most people will likely understand you even if you make a mistake, correct usage of less and fewer will undoubtedly be a testament to your linguistic proficiency. So, next time you put pen to paper or speak in English, remember this simple rule: countable, fewer, uncountable, less. But that's not all. Our gaze now turns to the boundless expanse of space. What do we know about the Sun's closest stellar neighbors? In our pursuit of distant galaxies, we often forget the mysteries hidden in our cosmic backyard. Alpha Centauri is the first thing that comes to mind, but believe me, the world surrounding us can be much more amazing and captivating. Prepare for a journey through our cosmic neighborhood, where incredible discoveries await. First, let's define what nearby means on a cosmic scale. Infographics don't always reflect the true picture, as distances between stars are measured in light years. Even Proxima Centauri, our closest star, is 4.25 light years away. To visualize this distance, imagine, if the Sun were an orange with a diameter of 7 centimeters, Proxima would be a cranberry no more than 1 centimeter in diameter, located 2,000 kilometers away from the orange, like the distance from Zaporizhia to Strasbourg. And this neighbor cannot be seen with the naked eye. If we mentally draw a sphere around the Sun with a diameter of about 30 light years, we'll find a constellation of diverse and interesting worlds there. According to Astronomy magazine, this sphere contains about 70 stars, including the Sun, grouped into 49 star systems. Stars prefer to live in pairs or even families of 3 or 4 stars, bound by gravity. 22 stars in the Sun's vicinity orbit in binary systems, and 15 in triple systems. Only half of the known stars in our stellar backyard remain solitary. But don't jump to conclusions. A solitary star might conceal a dimmer companion, as Sirius did for a long time. Notably, large and massive O and B spectral class stars are not found near the Sun. These giants, emitting immense amounts of energy, 1 million times more than the Sun, live for only a few million years. They don't have time to travel far from their birthplace, so they can be seen near nebulae, such as the Orion Nebula. The closest B-class star, Regulus, is 78 light-years from the Sun, and an O-class star is at least 366 light-years away. There are also no bloated orange and red giants and supergiants, which are in the final stages of their evolution, near the Sun's supergiants, once smaller but more massive than the Sun, at least 8 times, have already burned their hydrogen in their core and are ready to synthesize heavy elements before exploding as supernovae. Fortunately, none of them pose an immediate threat. Betelgeuse, whose explosion is anticipated, though perhaps in 1 million years, is 500 to 600 light-years away. Antares is 550 light-years away, and the closest supergiant is Polaris, located 300 to 400 light-years away. This yellow supergiant will mature into a red supergiant and explode as a supernova. In our cosmic neighborhood, there are not only dwarfs but also giants. The closest of them, Pollux, is only 34 light-years away. This star, approximately twice as massive and almost 9 times larger than the Sun, has already exhausted its hydrogen supply and transformed into an orange giant. Pollux will continue to expand until the end of its existence, but fortunately its mass is insufficient for a supernova explosion. Instead, it will shed its outer layers, forming a picturesque planetary nebula and leaving behind a faint white dwarf. Within 15 light-years of the Sun, stars of modest size predominate. About 2/3 of these stars have a mass half that of the Sun and belong to M-class red dwarfs, the coldest and dimmest stars in the universe. Paradoxically, none of these stellar tots can be seen with the naked eye, despite their relative proximity. The closest star to the Sun is Proxima Centauri, a member of the Alpha Centauri triple system. This red dwarf completes a full orbit around its more massive stellar companions in about 500,000 years. Currently, its orbit places it closer to us than its companions. Since this star has already been mentioned, we won't repeat ourselves. Proxima Centauri's more massive companions, Alpha Centauri A and Alpha Centauri B, appear as a single bright star to the naked eye. Alpha Centauri A is a yellow dwarf, similar to the Sun but slightly larger and more massive. In 2021, the discovery of a planet orbiting this star was announced, but its existence has not yet been confirmed. Alpha Centauri B is an orange dwarf, which is smaller and less massive than the Sun. The two stars orbit each other with a period of 80 Earth years. Alpha Centauri is one of the brightest stars in the night sky, surpassed in brightness only by Sirius, Canopus, and Arcturus. However, residents of the northern hemisphere cannot observe it. Instead of dwelling on Alpha Centauri, it's better to focus on stars that undeservedly remain in the shadows. First and foremost, this applies to Barnard's star, the second closest star system to the Sun and the fourth closest individual star. This red dwarf, located just 6 light-years away, holds the record for the fastest proper motion. This means that among all the stars in the sky, Barnard's star appears to be the fastest to an observer from Earth. Barnard's star is significantly smaller and less massive than the Sun. Its mass is only 14% of the Sun's, and its diameter is about 20%. In terms of size, it's more like Jupiter than the Sun, although it surpasses the largest planet in the solar system in mass by 150 times. Barnard's star is classified as a variable star. Its brightness periodically changes due to the appearance and disappearance of star spots during its rotation. Red dwarfs often exhibit instability, especially when young due to flares. However, Barnard's star is an old star, about 10 billion years old, so astronomers expected it to be quiet. Nevertheless, on July 17, 1998, Barnard's star delivered a surprise, demonstrating a powerful flare that lasted at least an hour and increased its brightness by more than 1.5 times. This bodes ill for potential worlds orbiting this star. In 2018, the discovery of a planet 3 times more massive than Earth was announced, but this discovery was later refuted, and the signal was deemed false, caused by the star's activity. Thus, for now, this superfast star has not revealed its planets, if they exist. Barnard's star's proper motion was first observed by American astronomer Edward Emerson Barnard in 1916 when he compared its position in a photograph with a 1904 photograph. It turned out that the star, now bearing his name, moves across the sky at a speed of 10 arcseconds per year relative to the Sun, which is about 90 kilometers per second. To cover a distance of half a degree, the apparent diameter of the Moon, it would take about 74 years. Thus, over a human lifetime, its position changes quite significantly, by about half the Moon's angular size. Most stars move across the sky at a speed of 0.1 arcseconds per year or even less. To see any changes in the night sky, one would have to wait several millennia. The rapid movement of Barnard's star is due not only to its relative proximity to us. Most stars in the Sun's vicinity, including our own star, orbit the center of the galaxy along nearly circular paths. However, Barnard's star, like Captian's star, stands out due to its non-local origin. These objects are emigrants from the Milky Way's halo, only temporarily crossing the galactic disk near the Sun. Their unusually high speed relative to us is explained by a significant difference in their galactic orbits compared to typical stars in our neighborhood. It is noteworthy that Barnard's star is gradually approaching the solar system and will reach its closest approach in approximately 10,000 years, when the distance between us will decrease to 3.75 light-years. Nevertheless, even then, it will not become the closest star to the Sun, ceding the palm to Proxima Centauri, which, along with the entire Alpha Centauri system, is also moving in our direction. In the array of celestial bodies, following stars are objects that can hardly be called stars in the full sense of the word. About 10 years ago, astronomer Kevin Luhman from Pennsylvania State University discovered a pair of cold and dim brown dwarfs located just 6.5 light-years from us. It's not surprising that these objects remained unnoticed for so long, as they are near the galactic plane, where the concentration of stars is particularly high. Detecting such faint and cold celestial bodies against the backdrop of bright stars is no easy task. However, thanks to the WISE Space Telescope, faint infrared radiation emanating from this pair of brown dwarfs was detected. The Hubble Space Telescope, in turn, conducted a series of observations of this system over 3 years and captured its components in several images. The two objects, each approximately 30 times more massive than Jupiter, orbit each other at a distance of about 3 astronomical units. In 2014, Kevin Luhman made another interesting discovery, finding a substellar object 7.5 light-years away from us. Unlike the previously found brown dwarfs, this object apparently has a mass of only 3 to 10 Jupiter masses and a very cold surface with a temperature ranging from -48 to -13 degrees Celsius. It should be noted that brown dwarfs are generally considered objects whose mass exceeds 13 Jupiter masses, as this is enough to initiate deuterium fusion in their interiors. Thus, the discovered object with a mass of up to 10 Jupiter masses is likely not a brown dwarf in the classical sense. Rather, it is some intermediate type of object, perhaps a so-called sub-brown dwarf. This term often refers to interstellar planets that formed like ordinary stars but could not accumulate enough mass to start thermonuclear reactions. Another version is that it is a regular super-Jupiter, ejected from its native planetary system as a result of gravitational interactions, and now wandering alone through space. Likely, new wide-field telescopes, planned for operation in the coming years, will help discover even more such objects in the Sun's vicinity. But our journey continues, and the next stop is the Wolf 359 star system, located about 8 light-years from the Sun and ranking 5th among the closest stars to us. This star, a red dwarf, is one of the smallest and lightest stars known to science today. Its mass is only 11% of the Sun's mass, and its diameter is 14% of the Sun's. Wolf 359 is a relatively young star, its age not exceeding 1 billion years. For a red dwarf, this means it has high activity and can suddenly flare up, increasing its brightness several times in a short period. The Hubble Space Telescope found no evidence of planets in this system. However, in 2019, the high-precision HARP spectrograph, installed on the European Southern Observatory Telescope in Chile, used the radial velocity method to detect 2 planet candidates orbiting Wolf 359. If these planets truly exist, the conditions on their surface must be extremely harsh. One planet is too close to the star, and the other, conversely, too far, for liquid water to exist on them. Further observations cast doubt on the existence of the planet closest to the star, suggesting that the detected signal might be false and caused by the star's own activity. The existence of the distant planet still requires confirmation. The existence of planets around the next star system in the Sun's vicinity, Lalande 21185, also known as Gliese 411, is much more reliably confirmed. This system, located 8 light-years from Earth and consisting of a red dwarf, contains at least 2 planets. Gliese 411b is a super-Earth whose mass exceeds our planet's mass by at least 2.5 times. It orbits its star in just 13 Earth days, being 10 times closer to it than Earth is to the Sun. Although the parent star is cooler than the Sun, it is still too hot on this planet for liquid water to exist. The second planet in the system, Gliese 411c, was confirmed in 2021. Both planets were discovered using the radial velocity method, which allows astronomers to detect tiny wobbles of a star caused by the gravitational pull of an orbiting planet. The mass of the second planet is 14 times that of Earth, and it is 3 times farther from the star than Earth is from the Sun. Given this distance, Gliese 411c is too cold for liquid water to exist. In 2021, the discovery of a third planet in the system, located between the two already known, was also announced, but its existence has not yet been confirmed. In any case, after the Proxima Centauri planetary system, the Lalande 21185 star system is the second closest system to us with confirmed planets. In the cluster of celestial bodies, Sirius rightfully holds a special place as the brightest star in the night sky, having long captivated the gaze of astronomy enthusiasts. Ancient Egyptians named it the Star of the Nile, as its morning appearance heralded the imminent flooding of the sacred river. However, in most cultures, it is known as the Dog Star, due to its belonging to the constellation Canis Major. Its proximity to the solar system, just 8.5 light-years, plays an important role in its dazzling brilliance, but we should not forget its intrinsic brightness. Sirius is a young A-class spectral star, which flared into existence during the time of the dinosaurs. Stars of this class are characterized by increased brightness, high temperature, and white color. Sirius is twice as massive and large as the Sun, and it emits 25 times more energy. Over the next 60,000 years, its brightness will steadily increase, after which the star will begin to move away from us and gradually dim, but it will remain the brightest star in the sky for hundreds of thousands of years. Despite the absence of planets, Sirius is not alone on its cosmic journey. In images obtained by the Hubble telescope, a tiny white dot can be seen next to it, Sirius B, a white dwarf the size of Earth but with a mass comparable to the Sun's. If Sirius A is the dog star, then Sirius B is often called the pup. Today, this dwarf is a companion to its larger neighbor, but this was not always the case. It is believed that Sirius B was once even more massive than Sirius A, representing a B-class spectral star, now absent from our vicinity. It was approximately 5 times more massive than the Sun, and more than twice as massive as Sirius A. About 120 million years ago, Sirius B transformed into a red giant, and then shed its outer layers, leaving behind only a dimming and cooling white dwarf. Incidentally, the same fate awaits Sirius A when it exhausts its hydrogen supply in its core within the next billion years. Thus, Sirius is a massive, bright, and one of the closest star systems to Earth, which explains its status as the brightest star in our sky. As we move farther from the Sun, we encounter more red dwarfs, among which the Luton 726-8 system, also known as Gliese 65, stands out. This is a binary system consisting of 2 red dwarf stars, both of which exhibit activity, especially the dimmer UV Ceti, whose brightness increases 75-fold during flares. A little farther from us are the solitary dwarf stars Ross 154 and Ross 248, unremarkable in any particular way, and so far there is no evidence of companions for them. However, the Epsilon Eridani system, next on our list of closest stars, is of great interest to science. Firstly, its main star has some resemblance to the Sun. Secondly, this star system is relatively young, only 400 to 800 million years old. Located 10.5 light-years from us in the constellation Eridanus in the southern hemisphere, it is an ideal testing ground for studying planet formation processes around Sun-like stars. To be precise, Epsilon Eridani is an orange dwarf, slightly less massive and smaller than the Sun, and one of the few stars in our vicinity that can be seen with the naked eye. In 1983, the IRAS Space Telescope detected an excess of infrared radiation from this system, which indicated the presence of a disk of material remaining after the star's formation. It is from this material, as is known, that planets are formed. Later observations by the Spitzer Space Telescope showed that the disk is fragmented, and its inner part is divided into 2 ring systems consisting of warmer material, resembling asteroid belts. The first, inner disk, is located at a distance of about 3 astronomical units from the star, which roughly corresponds to the distance at which the main asteroid belt is located in our solar system. The second, denser belt is located approximately where Uranus orbits in our system, i.e., at 20 astronomical units from the star, and represents an analog of the Kuiper belt. Just as Jupiter orbits near our asteroid belt, planets of Epsilon Eridani are believed to also orbit at the edges of its belts. The first of these planets, Epsilon Eridani b, was discovered back in 2000 using the radial velocity method. It has a mass of 0.63 Jupiter masses and orbits its star at a distance of 3.5 astronomical units, which is just outside the inner belt. The existence of a planet beyond the second belt has not yet been confirmed, but computer models predict its presence, as this explains the shape of the residual material disk. Astronomers believe that other, less massive planets may exist in the system, which may be discovered using telescopes such as the James Webb. In general, the study of the Epsilon Eridani system can shed light on many mysteries related to the evolution of a young solar system. Notably, the Tau Ceti star system was among the pioneers in the search for extraterrestrial life. It was on this system that the famous scientist Frank Drake directed his gaze, using the Howard T.C. Howard telescope, belonging to the U.S. National Radio Astronomy Observatory. Unfortunately, his efforts were unsuccessful. No signals from supposed alien civilizations were detected. Drake made another attempt, this time turning his telescope towards the Tau Ceti system. And although the result was again negative, these endeavors became an important starting point in humanity's quest to discover life beyond Earth. It is worth noting that Tau Ceti is a G-class spectral star, an analog of our Sun, being a yellow dwarf whose diameter is 79% of the Sun's. It is located 12 light-years from us, making it the closest single G-class star to the Sun. Interestingly, at the time of Drake's research, he did not have information that Tau Ceti is home to at least 4 rocky super-Earths, whose mass ranges from 2 to 4 Earth masses. Moreover, 2 of them potentially could have conditions suitable for the existence of life. Furthermore, 4 more planets are suspected in this system, awaiting confirmation. Astronomers involved in the search for exoplanets show particular interest in K and G-class stars, as they are characterized by the greatest stability. Orange dwarfs, in turn, surpass the Sun in lifespan and are capable of maintaining favorable conditions for the emergence and development of life for a longer period. Planets in the Tau Ceti system were discovered using the radial velocity method, based on observing the star's wobbles. Detecting Earth-like planets orbiting Sun-like stars requires highly sensitive equipment capable of detecting motion at speeds of only 30 centimeters per second. Modern astronomy has reached the necessary level of accuracy, but the main problem remains separating wobbles caused by planets from the natural surface activity of stars. To solve this problem, scientists apply complex models based on data obtained from several independent observations. In 2017, the discovery of 4 rocky planets orbiting Tau Ceti was announced. 2 of them are located too close to the star, even closer than Mercury is to the Sun, but the 2 outer planets appear to be on either side of the habitable zone. Tau Ceti e, a super-Earth whose mass is approximately 4 times that of Earth, orbits its star at a distance of 0.5 astronomical units. This distance is comparable to the distance between Venus and Mercury in our solar system, and a year here lasts 168 Earth days. Assuming this planet has an atmosphere similar to Earth's, its surface temperature could reach 70 degrees Celsius. However, its actual conditions remain a mystery. It is quite possible that this is a world resembling Venus. Tau Ceti F, another super-Earth whose mass is also about 4 Earth masses, orbits its star at a distance of 1.35 astronomical units, which is comparable to the distance from Mars to the Sun in our system. This planet is of particular interest because it is likely located in its star's habitable zone. But unfortunately, our knowledge about it is still very limited. Even if we assume that life originated on the surface of these planets, its existence could be fraught with certain difficulties, and not just due to stellar flares. Apparently, Tau Ceti is surrounded by a massive disk of material that contains 10 times more matter than the Kuiper belt in our solar system. This means that comets and asteroids must constantly bombard these planets, creating unfavorable conditions for life. To date, about 3 dozen planets are known to orbit stars located in the Sun's vicinity. All of them are certainly unique, as are their stars, but some of them are within the habitable zone, which, according to astrobiologists, is a key factor for the existence of life on a planet. Nevertheless, the most exciting world beyond our solar system remains Proxima Centauri b, a planet whose mass is only 30% greater than Earth's and which orbits its star every 11 Earth days. This planet's parent star is cold, so the distance from the planet to the star perfectly matches the concept of the habitable zone. While stellar flares certainly pose challenges for life on this planet, who knows what surprises the universe might have in store for us. Undoubtedly, the realization that the closest star to our Sun possesses an Earth-like planet is incredibly exciting. For now, we can only dream of building powerful space telescopes that will enable us to gather more information about this mysterious world.